That's a little awkward. Okay. So if you want, I haven't done this in a couple of weeks, but we should probably be like doing these. So like, if you want, put in the chat, like here's like your question of the day, and I'll take attendance with this as well. So yeah, it'll be fun to know what everyone thinks. Or you can share out loud if you want. Like Julia, like the easier question is, I guess, is like, what would you name your programming language? Not necessarily like what it would do, but like what would you name it? That's cool, Carol. Cobra, because it's like similar to Python, I guess. Andrew, that's really cool. That'd be like, I don't know, like, that'd be very helpful. Yeah, me neither. I don't know. I guess coffee, because like people really like coffee. Okay. Let's get into it. So today we're going to focus on something. Ball pie is a snake, because ball python's very cute. Okay. I'll research that. Okay, what I would name mine. I actually didn't think about this. I would name mine, I don't know. I'd name mine Popcorn, and it would be a database language, or slash like server side, like a server side asynchronous language. It's kind of like Node.js. That's what I would do. Okay. Okay, let's get into it. So today we're gonna kind of start talking about like feature representations. So over the past couple of weeks, we or at least last week, or a couple weeks ago, we started using like actual data in our machine learning models. And with that, we started like selecting features from our data to use. And then specifically in the data set that we used, which was that housing data set, it was all very like numerical. And today we're gonna look at how you can transform data into into features that you could use, since not all data can actually be used by a machine learning model. So let's get into it. So here, as you know, like in traditional programming, like your code is the focus of is like the focus of what you want to improve, right? Maybe it's like the time complexity or the space complexity if you've learned about algorithms. But in machine learning, that focus obviously moves towards like the models that you create and also the data. And so one way to improve the accuracy of your models is by improving how you represent your data. If that makes any sense. And so oftentimes, data comes into a form that our machine learning models, can't use. And so we need to like remember that our weights, which are those numerical values that we used before, right? When we did linear regression, those are stored as numerical numbers. So how would you use like a string? How do you use like string data in your machine learning model? Or how would you use dates if you are doing like multiplication with a numerical weight? So those are questions that you have to kind of figure out. And thankfully, people have figured it out before us. And so feature engineering is just that. It's converting like this raw data, like on this right side, and converting it into a like list or a list of features that we could actually use in our models. So is everyone following along? I just like kind of an intro.
Yes.
Okay. So when we look at like integer or floating point values, you don't really have to change that, right? So like in this case, there's num rooms, which is the number of rooms. And so you can just copy that over into a floating point, which is kind of trivial since it doesn't really matter. Like 6 and 6.0 are the same. But that's one way that you could change data. The more, I guess, hard or interesting way is what we call categorical features. And so these are inputs that have a discrete set of possible values. For example, there's a feature called street name, and it could only be, let's say it could only be 5 possible street names. And so since models cannot multiply strings by learned weights, we have to use feature engineering to convert the street name or the street name string into a numerical value that our model can understand and actually use as part of learning. So can anyone think of a way that I guess we could encode string data as like numerical values, but specifically like these categorical features?
I mean, if all the strings are different, how does it categorize them? Does it just call them like 1, 2, 3, 4 or something?
Yeah, I mean, that's one way, right? What I mean is that by a categorical feature is that the input could only ever be Charleston Road or North Boulevard or Shorebird Way or Ranksdorf Avenue. Like those are the 5 possible inputs that could be in the data. So like one way, as you said, is to just like map street names to like individual integers, right? So if we see the value Charleston Road in our street name, we just convert that to 0. Like we'd encode it as 0 in our data. Unfortunately, I guess, is that this doesn't really work. So if we, like, the reason why this doesn't work is like we have to go back to those basics of how machine learning models work. So let's assume that we've learned like a numerical weight of 6, like that's the number. remember we defined machine learning models, or at least the ones that we were using, as this relationship of y equals like w times x1 plus b. So like we multiply the weights times the input. And so when we do, we have a numerical weight of 6. When we multiply by 0 for Charleston Road, or 1 by North Shoreline Boulevard, or 2 by Shorebird Way, it's unlikely that there's like a linear relationship between like the price, like the house price maybe that we're predicting, and the input that we have. Right? So that's why we can't really encode it as single numerical values. The other like hard part is that what if you had like 2 inputs? Like what if you had a road that was on Charleston Road and North Shoreline Boulevard? Like it's on the corner, like a corner house. Like how would you encode that? So Andrew says, wouldn't it be equal to 0 if you multiply them all together? So just be Charleston Road. So Charles, so the roads aren't like the output, they're like the input. So it should be like 6 times like 0, 1, 2, or 3 plus some random value equals like our house price. So does everyone understand why that doesn't work? Okay. No.
Wait, so um, if you multiply each of them by like 0, 1, 2, and 3, then like the relationship isn't linear. The relationship between what though?
So it's unlikely that the relationship between like our prediction. So like let's say we're predicting house prices. It's unlikely that the relationship between house price and the road it's on is linear.
Okay. What's the numerical weight? Like
That's like
what?
the value that changes as we learn.
Okay, but what does the value do?
Uh, it's like, so remember when we did, that's like, this is like the whole machine learning. It's like the idea that as you learn, you like optimize your weights such that you get the lowest amount of error in your
Oh
prediction.
yeah. Okay.
So that's what it does. It's like the value that changes as you learn.
Wait,
The
so
meaning 6 has the value of 6 has no meaning, but we've learned, like the model itself has learned that if we multiply this by like our input, we get like the lowest prediction possible, or lowest error in our prediction.
so you just assign the numbers randomly?
Uh, no, we don't. So remember what so initially we start them at random values, but then we use a gradient descent and those um, loss optimization like algorithms that we learn, and then that would change the weights like incrementally until the error is minimized.
Okay, thank you.
Okay, cool. So the way that we fix this and how we encode almost all like categorical data is that we use like this thing called one-hot encoding. And so we create like a binary vector for each categorical feature. And for all values that are in like the feature, we set it to 1, and we set all of the other elements to 0. So here we convert street name Shorebird Way into this binary like list where the index corresponding to Shorebird Way that we define is given a value of 1, while everything else is given 0. This also means that if we have we can also encode multiple values now, such as, let's say we had Shorebird Way, and also, what's the other? We also had on Charleston Road. We could put like Charleston Road as 1 and Shorebird Way as 1 as well, while everything else is 0.
Then how does it tell the difference between Shorebird Way and Charleston Road?
It tells the difference because of its index in the list. And so, like potentially, if you had enough, street names, each of these like values in the list could have a corresponding weight that changes alongside of it.
How does it know what index is what though?
What index it is?
Yeah.
Yeah. So, okay.
Like when you convert the string into a feature, and if you turn Shorebird Way and Charleston both into like 1, then how does it know what 1 is what in the feature?
So I guess this goes a little deep, like my answer would go a little deeper into how like data types are handled in like a computer. So like regardless of how you like, sorry. So for a computer, Shorebird Way is like doesn't really mean anything. Like it means something to us as like a string or a like whereas like a location, but to a like a computer that doesn't know that or doesn't understand what these strings are, to it it's just like numerical numbers or like numerical values. And so I guess how I would say this is that it really never understood what Shorebird Way meant in the first place. And so by like doing this feature engineering and converting it into this list of zeros and ones, we're just like converting it into like a representation that it can actually use. Did I understand your question correctly? Or is it more about how would it differentiate between like different
ones?
Oh, okay. Okay. Yeah, so
I have a question. So you said that there's a binary vector for each categorical feature. So if it's like the number of rooms or in the number of bedrooms, like there's 6 rooms, is there 6 vectors or is there 1 vector?
so number of rooms and number of bedrooms aren't categorical features, since they have like there's an infinite amount of of like values that could be for a number of rooms, right? Since it's an integer. But street name, as we like defined, um, as we define like back here, can only be these 5 roads.
Okay.
So we wouldn't encode num rooms since it's a numerical value, but we would encode like street name since it's a categorical feature.
All right.
But the number of room is have limit. This may be the maximum number of the room is 10. So are you going to create a vector from like 1, 2, 3, 4, 5 to 10? Yeah.
No, not necessarily, since like to our computer or to our model, like there is no like limit to the amount of rooms. That's kind of just like a human, that's kind of like a human limitation on how many rooms could be in a house. But like numerically, there's no limit to how high num rooms could be. Yeah.
Also, when this title says one hot encoding, is it actually called hot encoding, or is that just no?
No, that's what it's called.
Okay.
I forgot like the dash. There's a dash in there. It's not like hot is not an adjective. Like one hot is the adjective. So yeah, that's my bad. Okay. And then I guess I could talk about it here a little, but you'd also represent categorical features in like another way. So let's say like you had like a paragraph of, I guess a paragraph is not very good, but let's say you had a string of like multiple words. If you did like the one hot encoding that we like represented here before, since there's so many like words or like possibilities like in the English language, you'd have a lot of zeros for each value that you encoded, right? Like most of these would be zeros in here, and there would only be like 3 ones if you were representing like dogs, wags, tails, wag tails. So one of the ways that we do this is that we just like remove all the zeros and have a sparse representation. The key here is that, or the key difference here is that we keep this cell number value as like kind of the index or like a numerical index that we still keep. And so that's just another representation of strings that we use in machine learning. So yeah. Cool. So I guess that's kind of what I want to go over. We should also look at what makes a good feature when you're looking at some. So there are kind of 4 tenets if you want to write these down. So one of them is avoid like feature values that are rarely used or have ones that are like unique to them. So this is the other one, is that you want features that have like obvious or clear meanings. And you want features that don't mix in outlier numbers. And you also want to make sure that the feature definition or like the numerical like definitions don't change over time. And so I'll go into some examples of what I mean here. So like good feature values should at least appear like, 5 times or so in a data set. That's kind of
What is the definition of a feature though?
Yeah, I'll get to that. So like hold on, you can hold on to your question, but okay, I'll get there. So yeah, so here a good feature would be like house type, where multiple examples would include the house type Victorian. But a bad feature here would be like unique house ID, where since it's unique, not many examples won't have like this house ID attached to it. So it wouldn't necessarily be a good feature since a model won't be able to determine the relationship between like this unique house ID and a predictive value, or like the thing that you're predicting. Okay. You also want features that have obvious meanings. And I think this should be a little bit, I guess, clearer, I guess. But with respect to name, like house, age, years, I think everyone can understand what that means, like just by reading it. And so that's why you might prefer it over something like house age. So in this case, like the house age doesn't really mean anything to us. Like, I don't know what this number means. You also don't want to include features that might have noisy or incorrect data inputs. So like user age years, no one's 277 years old. And so this is a thing that you might like clean yourself. But if you find that a feature has noisy data or incorrect, or another way to say that is like a lot of incorrect data inputs, you might not include it in your model. The third thing is that you don't want to include data set or features that have like out of range or discontinuities. So let's say that a feature holds like a floating point value between 0 and 1. And so having like quality rating 0.82 or quality rating like 0.37, those kind of make sense. But if you had like a data set that represented like the absence of a value with something like -1, which isn't between 0 and 1, that's not necessarily like a good feature overall. A way to make that better though is to create like a second feature along with it called like, is quality rating defined? And there you could have true false values to see whether like a quality rating is actually defined. And that would mean that your floating point values are still between 0 and 1, but you still contain the information of whether a quality rating is defined or not. And the fourth tenet is that the definition won't change. And I'll answer your question, Julia. And so what I mean by definition is that like its meaning over time, or the meaning of the value, like won't change. So here we have this feature called city ID, which is Brazil, Sao Paulo. And so that's a feature that has like inputs that won't change in meaning, right? Like so like yeah, like Brazil, Sao Paulo won't change, but this feature right here, which is inferred city cluster, so currently to us, 219 and Brazil, Sao Paulo are the same thing, but that representation can change easily if you had a change in your data, where now 220 might change into 219 might change to 220. something like that. So did that answer your question, Julia? I just want to make sure. Okay. So yeah, that's kind of, I guess, 30 minutes in. That's kind of what I want to talk about feature engineering. And that might be it. So next week, we're going to talk, obviously going to talk about classification and that kind of stuff. So, but don't leave yet, we still have more. I just want to talk about how we'll use the stuff that we learned here next week when we actually do some cool machine learning stuff. I guess this is cool, but it's not necessarily making AI. Okay. So we're going to talk about some theories, and we're going to talk about talking about nonlinear data sets. Actually going beyond like the linear regression models that we've been learning. So I guess here's the question, I guess. So we have these blue dots and these orange dots, sick and healthy trees, right? And so the question is, like, is this a linear problem? Could you draw like a straight line that, defines the boundary between these two sets? Nearly. I mean, yeah.
There's like that one blue dot that crosses over, but pretty much yes.
Yeah. So yeah, you're right. Like it would be a linear problem. Like the line wouldn't be perfect. You'd have like, it'd be a good predictor overall, right? And so here's another question. Could you separate this with a straight line?
Not really.
Yeah, right?
You have to separate with like 2 lines.
Yeah, I mean, yeah. I mean, that's what we're getting into. So like, no, you can't do this. This is a nonlinear problem, right? Since any line or straight line that you draw, singular straight line that you draw, will be a poor predictor of tree health, right? So here's like the thing. Like this isn't, that line with that black line in the middle is a bad predictor or bad separator between healthy and non-healthy trees. So to solve this nonlinear problem, we use feature crosses. And so a feature cross is essentially a synthetic feature that multiplies 2 or more input features together. And so in the grand scheme of things, this kind of feature wouldn't change. Like our linear formula or the linear formulas that define machine learning. And it doesn't change how we would calculate the value of weight 3. Except now we can actually like use x3 and solve something. So yeah, so this is what we're gonna kind of go into. Okay, we're gonna finish really early because I thought this would take a lot longer, but you guys are really understanding this right. So this is gonna be the exercise. I'll put this up. Wait, sorry about that. pressed the wrong button. Um, so I'll put this in chat for everyone to do. Oops. And so like kind of your exercise is to use this task. Oh, the answer's down there. That sucks. Whatever. But I guess you have the answer anyways. But you know, try, I guess, using x1 and x2 to create like a good representation of the data. Can you see this?
You stopped screen sharing.
Yeah, that's, sorry. I ran into something, which is weird. We share like a safe teacher login, and someone logged in. Okay. So I'll kind of go over this with you. So this is kind of the same thing that we did last week. Last week? I think so. Remember like this exercise thing? And so I guess you already know the answer, but here you can change like these weights manually. So if you put 0, put 0 here, and put 1. Actually, or any positive value, you get a really good representation of this feature of the, okay, you get a really good model overall, right? The orange corresponds to the orange and the blue corresponds to the blue. So yeah. You don't have to touch like any of this stuff yet. But we can see how this is kind of a good visual representation of how a feature cross would actually help us in predicting this, when if we only used like x1 and x2 by itself, we wouldn't get a very good line. Like this, it's actually really hard to see even like what the output is there. But you can see that it's like that the orange is still in the blue. But if we include like this x1 and x2, you can see that we actually get a very good separation in our two distributions. So that's like the strength that a feature cross can actually give you. And so I think a couple weeks ago, we actually discussed this. And I feel like I might have told you guys to do this already. But no, don't do that. Don't do that. Don't look at that. No one saw that. But so the more complex exercise is to kind of do that. So here, let me give you guys this. So here we have a different set of data, and I want you to try and make a good classifier for this, or at least a good enough one. So your tasks here are run the linear model as given and try different learning rates to see whether you can find any improvements. And so can this linear model using only x1 and x2 create a good model or produce effective results? Your next task then is to try add in cross product features or those cross features such as x1, x2 to try and optimize performance. And so which features help the most and what's the best performance that you can get to? And when you have a good model, examine like that output surface, like so that this background color. And so does it look like a linear model and how would you describe that model? And I know the slides are, you can see the slides in like the classroom, but please don't look at the solution. So I'll give you until 11:30 to finish this, hopefully. Toy around with everything, anything you want in here, actually. Yeah. You can be as, yeah, like get creative, I guess. Everyone can get to this website, right? It's in chat.
Wait, so what's the link to the exercise?
It should be the second one that I gave you. I sent it at 11:10 a.m. It's in chat. Or if you would like, you can.
Okay, I just searched it up.
Okay. Make sure that you have all like the right stuff. It's also in the Google Classroom. It should be, I put the slides up already. You can go to slide 21. Okay. Come back. If you're still working, I guess we'll go over solutions. But hopefully everyone's done. If you want to share, you can share if you want, out loud or in chat. What were your guys' answers to task 1, task 2, task 3? You want to speak up? Okay. So Carol says in task 1, the learning rate of 0.3 was all right. But do you think that the linear model produced like good results? Yeah, right. So I guess I'll try it as well. But if you just run this by itself, actually, let's reset. No. So the loss here is like 0.58, 0.78, sorry. 0.5, 0.58, doesn't matter. But it's not excellent, obviously. So I don't think that, x1, x2 by itself would work very well. Did you try, like in task 2, it says, try adding like those cross features, like x1, x2?
I tried adding x1, x2, and then x1, x2.
So x1 and x2 and then x1, x2, like this?
Oh, wait, no, I mean x1 squared, x2 squared, and then x1, x2.
Without these two?
Yeah,
Or,
can I do
or
that?
all? Yeah, yeah.
Okay.
So you did all 5?
No, I got rid of x1 and x2, like those two at the top.
Okay,
Uh-huh.
like that?
I did it a different way. I added I had x1, x2, x1 squared, x2 squared, x1, x2, and I got a circular thing.
Oh, yeah, so I tried that too, and the results were about the same, but it pretty much varied because, like, sometimes it's random.
Mm-hmm. So you tried this. They seem pretty similar.
X1, x2, you add that one in as well.
Oh, okay. Like this?
Yeah.
Okay, let's try this.
For me, sometimes I got a circular one like that.
That's cool. Yeah. So did you try like adjusting like the learning rate or anything?
Well,
I haven't tried that.
Oh, I didn't try that either.
Oh, okay. I guess I was like what's the best like I guess I wanted you to try out like different learning rates, different activations, this as well, this regularization and their rates. Maybe even change the batch size or ratio of training data to test data. But don't change noise. That's something different. I think according to the answer, the lower your learning rate is, the better, I think. Not that low. It's like this one. But yeah. Nice job. And so, yeah, when you examine the model output, it was a circle, right? And it's not a linear model. So here's the solution. So task 1 yeah, it's not a linear model. And so And then task 2 is that you could use both x1 squared and x2 squared. It says that x1 times x2 as a feature cross doesn't help, and setting a really low learning rate. And then the model output is not a linear model, it looks elliptical. So try this. Yeah, so it doesn't matter whether you used x1 times x2, it'd be the same. It'd be a circle. So yeah, good job, guys. Yeah, that was all I planned for today. I guess we're a little late or a little early for this class, but I kind of wanted to make this a little easier today in terms of content, because next week we'll really be starting to put everything together with classification and classification stuff like that, and actually using like TensorFlow and like seeing how you can actually create a model with TensorFlow instead of me like putting everything behind like these random like hidden cells. So yeah, if you would like, you can go if you want, but if you stay around, I will be able to review anything that you might have missed a couple weeks ago, and we can review before next week if you would like. But yeah. How many of you guys are gonna stay? Just to make sure, since you are free to go. Okay. I guess we'll just review some stuff. Let me get this stuff out. Well, should I record this? Okay. 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 So this is week 2. Just want to go over some stuff and review. So if you remember linear regression, I'll just go over this really quickly since we have 20 minutes. But if you remember linear regression, we had these line plots, and we essentially asked whether we could fit like the best possible line fit, and we tried to understand that many models are built on this principle that y equals mx plus b, or in our case, machine learning, it's y prime equals w1 times wx1 plus b, w1 times the x1 plus b, where y is that predicted label or prediction output, w1 is the weight, and x1 is the feature, and then b is like our bias. And so, as we did before, you can open this up if you want. We modified like our w1 and b to create a best fit line, and found something that's pretty good. And then loss, as we understood, is how close you were to the actual values. And so, as you can see here with this line, this best fit line, this has a higher loss compared to this loss on this other side. See? And then we understood that mean squared loss is one way of representing this error, where we take the distance between these points in the line, and we square it. And then we add those up and take the mean of those distance squareds. We did implementations of that. Does anyone remember how to implement that? I just want to. Maybe you can do it in NumPy now, since we did that actually a couple weeks ago as well. Okay. And so then we did implementations of MSE. So I think the better way to do this, as you remember, is to subtract these two NumPy arrays, then we square that list, and then we take the mean. We return that. That's kind of what we did. And so then when we reduce loss, we did this gradient descent algorithm, where we plotted loss and the value of weight. And we understood that there's always a minimum point. There's always a point where the loss is for a value of the weight. The loss will be minimized at that point. And so to calculate that on a computer, we use this gradient descent, where we set a starting point that's randomized, and then we step down this curve until we reach the bottom. Actually, yeah. Can I change this now? Yeah. And so if it's step size is called our learning rate. So a small learning rate takes forever to reach the bottom, while a large learning rate might step over the minimum. So one of our goals as machine learning scientists is to find a learning rate that steps just right and will reach the bottom efficiently. And so then we did this gradient descent activity. So it was kind of a quick overview of that. Hopefully that makes sense. But you can tell any questions if you would like to. the next one was week 3. Week 3 did something. Oh yeah, we introduced TensorFlow. And so, so here's like our basic understanding of TensorFlow. And so if you remember that we have these like upper echelons of the package. So this tf.keras is what we'll be using over this course. But yeah, there's a bunch of APIs there. And here's like a basic overview of NumPy. NumPy is our mathematics package in Python. And specifically, its key data type is the NumPy array, which is a kind of an array that doesn't change, but allows you to do really, really strong like mathematical functions with it. So you can like make 2D arrays, or you can like get random numbers, all that kind of stuff. And we did pandas and created like these data frames. And yeah. And then we actually applied our linear regression to our synthetic data. So in this case, remember we built and defined a training model. We obviously inputted our packages as well. And keyly, we tested around with the learning rate and epochs and batch size to create a model that would reduce its overall weight. And so, and then obviously try to make this line line up with the points there. So does everyone remember this? Or like is still confused about this part? I guess what's key to understand here, as well as before, is that we change these through values to create like a good model. And so these are, we call our hyperparameters, and that's what we change.
Okay.
Yeah. And then we did a bunch of tasks. Yeah. And then here's like kind of our summary of the hyperparameter tuning. And so as always, we should look to see that our training loss like declines somewhat steadily. And so as always, if our training loss doesn't converge or it doesn't plateau at a bottom, then we should increase the number of epochs. If the training rate decreases too slowly, we should increase the learning rate. And if the training loss like varies widely, as in it's jumping around a lot, we should decrease the learning rate. And so a good like thing to do when you're training is to lower your learning rate while increasing the number of epochs or the batch size. And so, as always, the ideal combination of hyperparameters is based on your data. So you always have to experiment and see what comes out as best. Then we'll go into this. So this is last week. And we went over overfitting, which to us is essentially making our model too specific and not generalized enough to new data. And so, as we saw here with this data set here, this is a really good model with a very low amount of error. But if when we added more data points, we ended up making a model that's not generalized enough to these healthy trees on the right and to these blue trees that ended up inside of these inside of the orange spots. And so the model obviously did a bad job of predicting new data. And so our way of solving this problem was breaking up our data set into training sets and testing sets. Right? And so we imagined as if we kind of sliced our data into a section where one section is the training set and the other section is the test set. You have to make sure that this training set, or just actually this testing set, is large enough to yield, or is large enough to actually test our data or test our model, and make sure that it's representative of the data set as a whole, such that when we test it, we're actually confirming how well our model is doing. So yeah, we did this visualization of, actually that visualization we did like 30 minutes ago. But from there, we understood that there's a training set and a testing set, but then we could go even further and split it up into training, validation, and testing, where we train the model, evaluate the model in the validation set, and then once we've created a good model that's on the validation set, we can confirm our results on our testing set. So yeah, that's that. And we did a bunch of predictions and stuff like that. So next week, we'll be using these training, validation, and testing sets as we'll be using these sets as we dive deeper into classification problems, which is kind of the next step in machine learning. And probably like the most interesting or applicable to real world applications. And then obviously we continue to use this idea of hyperparameter tuning to create better models. And then you obviously need the basics and understand that in the end, machine learning models are based on this idea of predictions equal weights times input plus bias, where weights and biases are changed to create better models as learning occurs. So yeah, that's kind of my quick summary of the last 3 weeks. Hopefully that was helpful. If you have any questions, as always, you can message me, email me, Google Classroom. Hopefully you can see my email. I think that's the thing. But yeah. As always, you were free to go. But yeah.
Okay,
See ya.
thank you.
See you guys.
Right, bye.